It's time to start. Welcome to the Thursday lecture of the second week of General Relativity. We started discussing manifolds, or no, we actually didn't yet manifolds, but vector spaces, and that will be the basis for our discussion of manifolds and differential manifolds. So we'll spend quite some time, as I announced already, introducing mathematical concepts. However, we will also today see already a bit of connection again to physics. I will again tell you what all that has to do with, for example, the example that we discussed at the very beginning of the course. But let me just continue where we essentially stopped last time. Towards the very end, I introduced the concept of an inner product. And I've also seen in the chat that there was maybe some confusion about the fact that I was, in the context of the inner product, also using the term metric. And indeed, an inner product in the context that we are talking about, and the way we'll use it later, it's quite usual to also call it a metric tensor. And as you remember, indeed, the inner product was defined by essentially specifying such a tensor that we called G. So remember, a tensor is exactly what we want when we want to define an inner product, because an inner product should take two vectors and assign to them a real number. And that's exactly what a 0,2 tensor would do. Okay, that's what we define. So remember, a metric tensor or an inner product is therefore a 0,2 tensor that is symmetric in the two arguments under exchange and positive definite. That was another property that we mentioned. And I will come back to that property because we have to weaken that for the purposes of treating general relativity. But before doing that, I would like to introduce a map, which I will call for the moment lowering map. And the map will be denoted by a little b as you have it in music. So it's this musical b that lowers the tone a bit, and that's why I call it lowering map, or maybe the symbol was chosen because of that. And what the map does, it takes a vector and maps it to the space of covectors. So you can already see why it's called lowering, because remember that objects in the vector space, the vectors, if I write them in components, these components have indices upstairs. Whereas the elements of the dual space, V star, if I write them in terms of components, they have the indices of these components are downstairs. So far, there was no real direct connection between the vector space and its dual space. There were just two spaces that we said have the same dimension and are in that sense isomorphic. But we couldn't take a vector V from capital V and understand it as an element from V star. However, once we have defined an inner product, and I will now assume that we have defined such an inner product on the vector space, there's a natural way to identify elements from here with elements from here. And the way this is done is as follows. So we take a little v, that's a vector, and just map it to the following function, namely g, v, and then take an arbitrary argument. So what I mean by this here is itself an element of v star. Namely, it's a linear function that takes as input something, which is, so this something goes where this dot is drawn and maps it to a real number. Because once I've inserted here something, of course, I'll get a real number.
Excuse me, Professor. I
Yes?
think your audio is a bit scratchy. I don't know how the people hear it.
Is it more lower than?
It was a bit scratchy, like when you talk.
Okay, let me briefly
I don't hear
check
any
what
of
I
that.
can do.
It sounds fine for me.
I now slightly changed the settings. Is it better now?
Yeah, okay. Looks like for people is fine, so might be just me.
So maybe it's a problem only on your side. Okay. So yeah. So please, if or if more than you have a problem, maybe you just write that in the chat, and then you can tell me whether this is a more general problem. And in that case, I will probably change the microphone. But let me for the moment continue, and please interrupt me if the problem persists. Okay, so this new element that we defined here, I will call V with this little b upstairs. So this is not an index. This b is this symbol that I also used for a map. So this is just notation. So this v is a vector, and this is a covector defined via this map. Okay, so far that's just a map, and we will later see why it's useful, but it gives us now a way to identify elements from V with V star. And let us see what this means in components, because that gives maybe some insight in what this is. So first of all, G is a tensor, as we said, a 0,2 tensor. A 0,2 tensor is defined by components with two indices downstairs. And if I write it in terms of the basis, and the basis are these tensor products between EI and EJ, or epsilon I and epsilon J, then this looks like this. So this is just the expression for G in terms of a fixed dual basis. Now, I could ask, what is now the expression for this? So given a vector V, what are the components of VB, of this dual vector? Because it's a dual vector, an element of V star, the components have indices downstairs. That's why you see this I downstairs. And what I claim is that the vector or these components are just given by multiplying this Gij, so the components of the metric with the original component, or with the components of the original vector. So that's so far just a claim, but it's very easy to verify this claim. So let me just put a small proof. Maybe it's almost a bit exaggerated to call this a proof, but very little calculation. So the trick here is always, if you want to understand what is a vector of the dual space, what does it do, like this VB, then what you should do is just apply it to a vector, because that's what the dual vector does. It eats vectors. So you just input to it the vector W and see what happens. Now, first of all, what I do is I just write VB in terms of components. So that's generally true. I didn't use anything except the fact that VB is a covector, so I can write it as this. That's just the expression for VB. And now I feed this W into this object. And now what I got is what you see here on the screen. That's just the rewriting in that sense. Now, what I already have is a expression for VIB, or let's see, okay, maybe what I should do is now, so I test whether the expression we got is a good one. So we get, I apply what I've here, Gij to Vj, that's the expression for the components of VB. And I apply epsilon I, or yeah, maybe I do that immediately. I apply so I evaluate this, but what's this? This just takes the W component from, or this takes the component I from the vector W. So what this object is just Wi. And now you see, indeed, the expression now corresponds to GVW. That's what this here is, by the definition of what G means. So we have indeed obtained the correct result, because what we wanted is to prove that if we take this object, maybe I should have written here what we want to prove. So remember, what this here tells us is essentially that if I take VB and apply it to some W, I should get GVW. That's what this definition means of the map B. And indeed, that's what I got here in this proof. So therefore, I've verified that this expression for the components of VB is correct. Okay, so that was just a very little calculation to see how we work with these objects. So remember, the trick is always apply dual vectors to some arbitrary vector W and see what it does. Now what we can also do is define, I mean, we have seen this musical B, which lowers the frequency of a sound, and there is of course also the opposite. This is called sharp, and we define it as the inverse of the map B. So therefore sharp is an operation that takes vectors from V star and maps them back to V. Just the inverse of B, so it therefore raises the index, if you like. So if I take an object phi here from V star, this object phi will be mapped to something that I will call phi star. And phi star is now an object from V, so its components have indices upstairs. That's exactly what justifies this terminology, raising map, that I will use in the following. Now let's see what the components are of this map, or how I can describe this map. So let's just take an arbitrary phi and again apply this raising map, the sharp, and let's see what the component I is. So clearly, because the original map B, the lowering map, is a linear map, it must also be the case that the sharp map, the raising map, is a linear map. And for any linear map, I can clearly write that the components of the outcome of the map are given by some object G, some coefficients, which I call G bar. This is a priori not related to G. I don't yet know what it has to do with G, but I call it G bar, times the components of the original vector. So that's just what I wrote here, is just to say that this map here from here to here is essentially linear, and these are the coefficients of this linear map. So now to find out what G bar is, what I do is I do the following trick. I just insert for phi some VB. So I set essentially phi equal to VB. That's a possible choice. And then, of course, if I apply the sharp map, so then if I now have phi sharp, this is now V, B sharp, but B is the inverse of sharp, vice versa, so I should get back V. So let's use that condition. So let's now evaluate this expression here, or more precisely this expression, using this choice for phi. What do I get? So I take this choice for phi, which is VB. I take the sharp, and now I evaluate the i's component. Now just use the expression that I've given, the fact that it's a linear map, so I have these coefficients, G bar, and then I still have VB, that's the object that I inserted, and from that, according to the rule above, according to this rule, I should just take the J component. So that's what this rule tells me. And now I can conversely again use the rule that defined VB. So remember, you have it here on the right-hand side, VB is given by the expression, let me mark it for you, by this expression here. So I insert this expression in my calculation. Of course, I need to use other indices to avoid a clash here. So let's call them J and K instead of I and J. And then, of course, the V should have the index K upstairs. And what we want, what should hold, according to what I told you here, this should be equal to the vector v, or more precisely to the ith component of the vector v, because here I only evaluated the ith component. So for this to be true, it must necessarily be the case that this thing here is the delta function of I and k. Only then this exclamation mark equality can hold. So therefore, what we found out is we now know something about these coefficients, which I just introduced as something new. I just said there are some coefficients. Namely, we know that the coefficients of G bar times the coefficients of G should give the delta. So if I interpret these coefficients as the coefficients of a D times D matrix, where D is the dimension of the vector space, so remember the indices run over the different basis vectors or the dimension, then this thing just corresponds to the statement that the matrix defined by G bar times the matrix defined by G gives the identity matrix. So therefore, G, or the Gij, are the components, or the entries, maybe I should call them entries, because it's a matrix. The entries of the inverse of the matrix that is defined by the entries of G, J, K. So that's what this thing here says in words. So in other words, I can calculate this Gij with indices upstairs from, if you give me the metric, by just taking the matrix inverse. And that will be an operation that we will do very often. We will very often need this inverse map, this sharp map, that one here. And so to get it, we now know we need to take the coefficients of the metric, interpret as a matrix, invert this matrix, and then interpret the entries of that matrix as these coefficients, or take the entries of the matrix as these coefficients. Now the convention that is used, because this occurs very often, this will occur very often, is that we drop the bar. So we just write Gij. And so you see we have now two things. We have Gij and we have Gij with indices downstairs. The way they are related is via this inversion. So we get from this from the metric, which is defined by this, to this object here by inverting a matrix. So that's something that we will come back to later. For the moment, I will stop here because we will only use that once we have introduced manifolds. So for the moment, you should just remember now from what I told you, once we have defined an inner product or a metric tensor, we have a map defined, or that allows us to connect V and V star. And this map is essentially given in one direction by the coefficients of the metric tensor, and in the other direction by the coefficients of the inverse matrix defined by this tensor. Okay, so one thing I should mention, however, already now, is that we will later do the following. We will replace the requirement that the metric is positive. So remember, we have this requirement that if we insert V into the metric twice, this should always give something positive if V is not 0, by the weaker requirement that the map that we defined, namely the map B, is injective. So it can be very easily verified that if the matrix Gij, if the matrix Gij is positive definite, so if it satisfies this criterion here, then the map B that I defined here is actually an invertible map. I didn't say that before, but I assumed it implicitly, otherwise I couldn't have defined this sharp map. But this can be shown very easily. However, it turns out to be a too strong requirement for general relativity for the purpose we will use this metric for, to require that it's always positive. But it will be sufficient to do whatever we did here, namely to define these maps, and in particular to define the inverse map, if this map is invertible. So we just put this as a requirement instead of the positivity. So in the future, therefore, when I talk about the metric tensor, I usually mean such a 2 or 0-2 tensor that is symmetric and such that this map is invertible. Now we will come back later today to the use of this Gy. We should allow it to be negative, but let's for the moment leave that topic unless there are questions. And because I would like to start very soon now with the actual differential geometry part. And then, as I said, come back to the metric for a moment. Are there questions up to this point? Okay, this doesn't seem to be the case. So let me, however, because there were actually many questions last time in the chat, as well as after the lecture, and they were very good questions. So thanks to those who asked these questions. And two of them are probably relevant for a broader audience, so to speak. And I want to, before I now continue with the differential geometry, briefly say something about these questions. So the first is has a very short answer. The first question was about the fact, so these are now just comments, about the fact that I said last time we cannot add tensors of two different types. So if you have, for example, an S and a T that are both, let's say, 1-1 tensors, then we can, of course, add them. And I think I never actually defined addition, but I just said it's the natural one. The addition is defined in the following way. So whenever I have to define a new tensor, this is S plus T is now a new tensor, I can do it by telling you how it acts on its arguments. And because it's a 1-1 tensor in this example, it takes as argument a covector phi and a vector v. And now if I tell you what this gives, then I have fully defined the tensor S plus T. So here the definition is just, it should be S fed with these arguments plus T fed with these very same arguments. So that defines S plus T as a tensor. So it's a coordinate independent definition, incidentally, so I didn't use any basis or so to define this. Now, if you suppose S and T were of different types, so let's suppose S is still a 1-1 tensor, but T is, for example, a 0-2 tensor. Then I couldn't write this thing on the right-hand side because, of course, I would have now, first of all, arguments for the S, the phi and the v, but if T is a different tensor, for example, a 0-2 tensor, it takes two vectors as inputs. So, but I don't have this vector. I would, of course, I could somehow, for example, define this, now say, okay, let's now take here a third argument, W, and put here V and W to T. But then it would no longer be a linear map because the W would only appear here, but not here. So if I scale the W, the whole thing would not behave correctly. So in order to define addition for tensors, I really need that they are of the same type. So that's just one comment I wanted to make. It's probably very easy to see once you have thought about this, but it's certainly worth trying once to define something else. And then there was another question. So let's call that comment 1, and then the other thing is comment 2. That was a question I never actually really thought about before in detail, but it's something actually which is quite basic, so probably I should have. The question was the following. We have defined basis transformations via coefficients lambda ij like this. So this is, we just said a new basis vector can be expressed in terms of the old basis vector. And then someone asked, what if I interpret these coefficients as the element, or if I interpret these numbers? So a priori, these are just numbers, they're real numbers. But of course, they are arranged in a particular way with these indices. So it's very, let's say, immediate to try to interpret them as a tensor. So what would it mean to interpret them as a tensor? I would define a tensor lambda and say, okay, these are the coefficients of the tensor. Now, if I have coefficients, I need to put the basis. Now, the first index is downstairs, so the basis element should be upstairs. We know that this has to be the case for consistency. And then the second basis element should be something with the basis, with the index downstairs. So it's a basis of the original basis element of the original space V. However, this would not be a very natural thing to do, to write this, because when you look at what this definition here does, then the I refers to a vector in the new basis, tilde. So whereas the J refers to a vector in the original basis without the tilde. So maybe a more natural thing to do would be to say, okay, let's also put the tilde here on this vector. And now let's see what this whole thing is. And now if you, okay, that's now well-defined tensor, and you can try to understand what it does. And to try to understand what it does, you can first of all use linearity and just write epsilon I at the beginning, and then the lambda ij. So put here the tensor product and then write this. But then when you go back to this here, then you see that this is nothing else than just writing EI tensor EJ downstairs. So now we have two elements with the tilde. And if you ask yourself what this is in terms of a matrix, then it's essentially an identity matrix. Oh, sorry, I should have written here I, because the other things collapse. So here should be an I at the end. So that's just, again, if you now translate it back to a matrix, an identity matrix. And indeed, you can interpret this thing as an operation, and it just corresponds to the identity operation. It takes, I mean, if you let it act, for example, on EI, or on any, let's say on a basis vector E tilde K, then this thing just only takes the element K, and this will again produce an epsilon K. So it produces whatever you put as input, or I mean, it depends on whether you interpret it as a map from V to V or V star to V star. You can do both. You can say that this whole thing acts with this on whatever is given, or with this, but in both cases you get the identity. So in other words, what this conclusion of that is, if you take these coefficients and interpret them as the coefficients of a tensor in the right way, namely in that way, then this is just a fancy way to write the identity operation. So in other words, the basis independent way to write the lambda is just to say it's the identity. But this makes sense because the only thing we do here is to transform into a different basis. And of course, transforming in a different, so in a basis where in the original space from which we start, we have one basis, and in the final space, or in the same space, but in the target should be expressed in the tilde basis, then things look more complicated. But you could therefore interpret these lambdas as just the matrix elements of the identity if you take the input to be defined with respect to the original basis and the output to be defined with respect to the tilde basis. Okay, so that answers these questions that came up. I hope these answers are useful, because it's kind of generally useful to play a bit with these things to get some feeling of what they do. But now I think it's time to move on. unless, of course, again, there are now questions. I'm very happy to take questions before starting with this new chapter, but the new chapter will be the one I announced now several times. It will be a chapter on differential geometry. But are there questions? So it's now really a very good time to ask questions about the part so far, about everything with tensors, tensor products, basis transformations. I've now seen quite a lot of things that you have probably seen before. And it could be that either because of the notation that is unusual or because everything was probably fast in case you haven't seen it before. Yes?
Yes, I have a question about the tensor contraction. You said the tensor contraction contracted the R plus 1, S plus 1 tensor to a RS tensor. And it's a bit difficult for me to imagine it because if we have like a 1-1 tensor, then we have in the end, by the contraction, we have an element in R, which is a 0-0 tensor, and this is correct, right? But if we have a 2 tensor, and then we do the contraction, then we get 2 real number. And what is the composition, the calculation between these 2 real numbers so that one of them is in V and one of them is in V star?
Yeah. Okay, so let me maybe just make another example of that, because the example I had was indeed a very, maybe, or too basic one where you don't see that. So tell me what kind of tensor I should start with. So you just give me a number R and S, and I will take that.
Let's say 2-2 tensor.
Okay, let's say a 2-2 tensor. So let's do that. Let's suppose we have a tensor that we call T, and it's a 2-2 tensor. Now I can do things either in components or in a component independent way, but let's first start with the components because that gives a different view. So if it's a 2-2 tensor, it has, of course, 4 indices. Let's call them I, J, and M and N. And now if I take the contraction of such a big tensor, I need to specify more than just saying that I take the contraction. That may actually have led to some confusion because in the simple example, this is not necessary. I could either, for example, contract the first part of the tensor with that thing or something else. So let's do that. So it would be a trace where I contract 1 and 3. So I write this with the first and the third index. So if I apply this contraction to the tensor and now ask myself, what is now the index of the new tensor? And what are the components of the new tensor? Maybe the best thing is to actually keep the indices that are not contracted before. So I write, for example, a J, which was not affected, and the N. And then this is defined as T, I, J, I, N, which means that you actually sum over I and leave the J and then constant. So one way to think of it is that the example I gave of a 1-1 tensor is what you do with each coefficient. So if you have more coefficients, you just fix them. I mean, here we have not only I and M, but we also have J and N, but you just don't touch them. You just write J and N. So they will be left, these indices, and do the sum as if it was just a 1-1 tensor for those indices, but write the other indices just there. So if you compare this to the case that we've seen, let me maybe put that here below. So we have seen, let's say, another tensor, let's call it, let's say S, which is just a 1-1 tensor. So in this case, if I take the trace of S, then I would just have S, I. And so if you compare this to that, you see the only difference is that all the other indices that were not affected by the trace, because I have to here specify which indices or which arguments the trace acts on, they just stay there. So this is just a way to do it. Now I'm not sure it actually answers fully your question, because you probably also want to understand what is the intuition behind these trays. But
so the natural pairing is just for one element in V star and one element in V. So we pick one element. Because before I thought it's if we have two elements in V star and two elements in V, then we pair them each, then we get two.
Yes. So you may also do that, but usually one always takes one pair. And then if I would want to, for example, also combine now the second J, and then I would need to write that. So one thing I could do now is to say, now I want to contract also the others. So I just take again the trace of that. So I apply, for example, in this example, I could, let me write it again. I could say, I have already taken the trace of 1 and 3, T, and this still has now two arguments, and I take again the trace of that. I again pair 2. But now I have only 2 left, so it's clear which ones I pair. So in this case, I get T, I, J, I, J, because now I paired both. But I need to specify the pairing, and the result I get is actually different depending on what I pair. So if I, for example, paired first 1 and 4, then I would have gotten a different tensor than when I paired 1 and 3. So I need to specify which ones we pair. However, what you are not allowed to do is to pair 2 upstairs or to pair 2 downstairs. You only need to take the trace of 1 up and 1 down. And the reason for that is that we proved that this trace is a basis independent operation. Now I've described it in terms of a basis, because when I write indices, this implicitly assumes, of course, a basis with respect to which these components are defined. But we have seen that the original definition doesn't involve a basis, but that's only true if we have essentially in the tensor 1 contravariant input and 1 covariant input that we sum over. But as long as you do that, then you get something basis independent, which means it's still a valid tensor. Does this help?
Yes, it has very much. And I have a question about this lower function that you just introduced. Well, is it the base of a vector space have the indices down? And the vectors in this vector space have the indices up? Because, yes.
So, you're now talking about the B operation or the
I'm talking about the lower and lower.
The lowering, this one here.
Map.
You're talking about that one.
Yes, and in V star, the bases, they have the indices up.
Yes, that's right. So you always have to, okay, the thing to keep in mind is probably the following, which is often leading as well to confusion if you see it first, that if I take an element phi from V star, then if I write phi in terms of a basis, I would write it like that. First, the components of it have indices downstairs, but the basis elements have indices upstairs. So if I call it lowering operation, you should maybe understand this, that the lowering refers to the, not to the basis elements, but to the coefficients. So the new object, the phi, has now the coefficients with an index down. But you are absolutely right that the basis elements have indices upstairs. But the reason one calls it lowering is that usually when you work with these objects, you just fix the basis. I mean, you may fix different bases, but you say, now I do everything in this basis, and then you are talking about these objects. And so on the left-hand side, you would describe the object V by giving the components Vi, and you describe the object you get here, namely the phi, by giving the components phi I downstairs. And so the lowering really refers to these components with indices up and with index down. So that's at the end just a terminology, but it's indeed confusing if you think of the basis elements. They are not the reason why we call this lowering. They're the coefficients.
Okay, thank you very much.
Okay, you're welcome.
So
thanks
there
a
are
lot.
some questions from the chat.
Yes.
So there was somebody asking whether you could just scroll down a bit the right part in your
Yes, sure.
iPad.
Yeah. Okay, that's an easy question to answer. Okay,
and
good.
Then there are more questions. There was maybe one which is linked to the same question as before. When you were talking about the trace, somebody asked if this is equivalent to the partial trace.
Yes, okay. I don't know where you have seen partial traces, but yes, you can understand it in that way. Yes, that's correct. I mean, I don't want to maybe go deeper into that, because for those who haven't seen partial traces, that would not be very informative. But if you have seen the concept of partial traces, then you can understand the trace operation in case you apply to a tensor which is of higher degree than 1, 1 as a partial trace. So this occurs often in quantum mechanics. There you could write the density operator of a joint system consisting of two parts as a density or you could understand it as a 2, 2 tensor. And if you take the partial trace, you get a 1, 1 tensor. So that's correct, yes.
Then there is a bit longer question. Before that, it just says the atmosphere is very relaxing in this course, but then he asks, if we have a 1, 1 tensor which takes a covector and a vector and maps it to the real numbers, we also can say that a 1, 1 tensor can be represented by a matrix, but a matrix can not only take covectors and vectors, but can also take only a covector and map it to another covector. So a matrix that only takes a vector and maps it to another vector is not a tensor, but what is it?
Okay, yes.
Yeah.
So I think this is actually something that is worth commenting on, really. So thanks a lot also for that question. So as I said, I really appreciate questions, because actually the material I've planned to cover is less than, or is less than I can cover if I only speak. So there's really time calculated in for your question. So that's just to make sure you don't hesitate to ask them, but I see there are indeed these questions. So let me briefly also comment on that one, because that's really important for not getting confused with these things. So I think if I understand the question correctly, if I could have a tensor like, let's again say a 1, 1 tensor, and as we just said, a 1, 1 tensor has one index up and one down if I write it in components. Now I can, of course, write this as a matrix. So I can actually really take a matrix, and here the first component would be 1, 1, and then usually the convention, I think that I mentioned last time, is that the row is indicated by the first component, and the column is indicated by the second one. So I would have here entries of that type. So the last one would be PD, and of course there could be many in between. Now, a tensor, or what this tensor, if you just go back to the tensor, what the tensor does, it takes as an argument a phi and a v, a covector and a vector, and maps it to a real number. Now, if you see it as a matrix, it's very natural to interpret this matrix as a map, for example, from V to V. And that's what you would often do. If you see this matrix, you say, oh, that's a matrix, I can multiply it with a vector, and then it gives me a new vector. And indeed, you are allowed to look at it in that way. And let me maybe briefly say what that means. So what you could do is to say that if you now go to the coordinate independent thing here, then if you take, so let's see what happens if I take T and I somehow only fill it with one argument. So I leave the first one open and just put a V as the second. So this object that I obtained here is by itself now a map that would go from V star to R. So in other words, this object that I've just defined is actually an element of the dual space of V star star. But we said already that V star star is actually isomorphic to V, so we can identify these two things. So you could indeed say that if you can interpret T, so what, or maybe I'll write it like that. So if you have some vector V and do this thing that I just did, so I applied T in that sense. So I defined a new vector, the transformed one, W, let's say, as the vector that is defined by this isomorphism. Let me call it like this, because it's not really an element, but by this isomorphism. Then T defines really a linear map. So it takes a V and produces a W. If you now, I mean, I will not do that now, but if you now sit down and write down what is this linear map in terms of components, in terms of a matrix, you will find that it's indeed exactly that matrix. So in other words, it's correct to say that if you take a 1-1 tensor, it can, and write it down, the components as a matrix, then you can interpret this matrix as a map from V to V. But this is only true for a 1-1 tensor. This is now important. If I did the same thing for a, let's say, 0-2 tensor. So for example, we just saw that G, the metric, is a 0-2 tensor, and I can again write it as a matrix. I can write it G11, then G1D, and so on, GD1, GDD. So it's again a matrix. And now you would say, oh, naturally, I can again interpret this matrix as a linear map from the vector space V to V. But this is actually not the case. So this will not be true. And what do I mean by it's not the case? So here, when I did this whole thing with T, I could define a linear map in a basis-independent way. So I told you what this linear map is, namely that one, without invoking a basis. Now, of course, I could just say the linear map is this thing multiplied with the components of the vector, but I cannot write this in any way as a linear map from V to V. Actually, what happens if I do the same, I say I feed it with V and leave the other thing open, for example, then I have actually an element from V star. So this means that you can interpret this matrix here as an operation that goes from V to V star. So it's again a linear map, but not one from V to V, but one from V to V star. Now, you could say, well, what difference does this make? I mean, once I interpret it as an operation from V to V and once as an operation from V to V star. The difference will become relevant once you want to transform the whole thing into a different basis. So if you have now given this matrix and I tell you, please tell me what this linear map is in a different basis. Then if you just, if you know that it's an operation from V to V star, it will transform differently than if it's an operation from V to V. That's exactly reflected by the fact that these are mathematically very different elements. This G is a 0-2 tensor, and we know that 0-2 tensors transform differently, or the components of them transform differently than the components of a 1-1 tensor. So let's say the summary of this is you can always interpret tensors as linear maps, but depending, I mean, if the total, I mean, even of more complicated ones, but the map will not necessarily be a map from V to V. It will sometimes be a map from V to V star, or even from V star to V. That depends on how you see it, or from V star to V star. For example, a 2-0 tensor could be interpreted as a map from V star to V star. So that's why it's very dangerous, and that's maybe the take-home message, to just write things as a matrix and forget where they came from. Because now, if you just have the matrix and wouldn't any longer know that the indices here are downstairs or upstairs, you would not know how to correctly transform these matrix elements into a different basis. So I hope this gives you some insight. That's maybe even going beyond answering that question, but that's something you should anyway know, I guess.
Okay, thank you.
Okay, I think it's now actually a good time to make a break. I will, of course, also take questions during the break. But I think given the time, it's we should now stop for 10 minutes, which just means I will continue with the new chapter, which I already now almost started, namely the one on differential geometry at, let's say, at 1 o'clock. And until then, I'm very happy to take more questions. And as usual, those who leave, please be back at 1. Okay, but I guess there was another question, or at least that's what I heard.
There is one in the chat. I don't know if you want to read it, or I can read it for you.
Yes, please, because I cannot read it.
Okay. So it says, I would also have a question about change of basis, namely, I am confused about the way we define co- and contravariant transformations. Say, I would like to check whether an object transforms contravariantly. I would apply lambda inverse, but who tells me I am not in a tilde basis and would thus have to use lambda? And if I cannot distinguish which one to use, I also cannot conclude if my object indeed transforms contravariantly or not.
Okay, so let me maybe answer the question by first saying something general, so to speak. So it's quite usual to, or quite useful to think of two different, let's say, ways of talking about these mathematical objects. And I did that actually in a way. So one is basis independent and the other is basis dependent. Now in the basis independent world, I should really avoid ever talking about the basis. Whenever I define something or talk about something, it should not involve a basis, which means in particular, I'm not allowed to talk about things like Tij. This doesn't occur here because the Ij means that this object is defined with respect to a basis element Ei and Tj. So that should really go onto the other side. So on this side, I just have tensors, for example, T and G. And on this side, let me maybe put them not on top of each other, T and G. Now, on the right-hand side, I have basis-dependent statements. So I have something like Tij or Gij. Now, the connection is made via the basis. So if I want to know how are they related, then what I need to do is to remind myself that T is equal to Tij, the coefficients times the basis elements. And if it's, for example, a 1-1 tensor, then the basis elements look like this. And here in the case of G, the connection would be that I say G is Gij times epsilon I epsilon j. Maybe I could even have much simpler objects, just the vector V. And again, the coefficients of the vector are here, Vi. And of course, here we have seen this connection as well. It's just Vi times Ei. Now, because the right-hand side is basis independent or basis dependent, there will, depending on the basis, be different ways to represent it. So I could also have the T tilde Ij and the G Ij tilde and the V tilde I. And so again, they are related exactly the same way to the right-hand side. So if I want to go here, for example, I just write that T is equal to T tilde Ij, Ei tilde epsilon j tilde, and so on. So maybe do it here, because that's maybe some example where I can continue. V is now Vi tilde Ei tilde. Now, what you should notice first when you're talking about basis transformations is that a basis transformation is something that only, or a coordinate, I mean, a change of basis is only relevant here on the right-hand side. If if there's a basis transformation, there's nothing to do here. So in other words, the tensor T or the tensor G or the vector V don't change on the basis transformations. It's only the coefficients. Now, your question, if I understand it correctly, is how do you find out how to do the basis transformation? Now, of course, what one should first ask, what is really the goal of the basis transformation? The goal is, of course, or the requirement is that if you do a basis transformation, what you do, you change this part, for example, by this part. And of course, if you, on the left-hand side, the T is the same, that doesn't change. So if you change the E and the epsilon to an E tilde and an epsilon tilde, in order to have the same T, these coefficients T and T tilde have to change. So the basis transformations are mathematically defined exactly in that way that the change imposed by going from here to here will be compensated by the change in the coefficients. So that defines the rule. So if I haven't told you what the rule was, it would just, again, you could reconstruct it by exactly this criterion. Find the map from Ti to T tilde such that the left-hand side of this equality remains the same. Now, once you do that, this calculation, you will find a rule. And the rule is essentially always the same. Namely, it's the following rule. And I think that's at the end answer how to decide. So if you have a coefficient, let's say, or suppose you have something like that, a Vi upstairs, and you have some Vi tilde, and you want to know how they are related, then it's kind of useful to remember that there are essentially only two rules. One is that if the index is downstairs and you go from V to V tilde, then you don't do anything with inverses. If it's upstairs, then it's usually the inverse that is relevant. So that's just a way to remember. So you say, if I now want to express that, I want to know V tilde I. The only thing I need to remember is that there's this lambda that will occur, but because it's an upstairs thing, therefore a contravariant thing. So contra means it's somehow more complicated. So I need to the -1. And now I need to see what the indices are. So it has to have an index upstairs because what it's producing is an index upstairs, and it takes some index downstairs from what has been given originally. And so that would be that transformation. If I, for example, transform G, then again, a priori may not know what to do, but now what I have to think about is both indices are covariant. Covariant means I don't take an inverse. So I need to produce an index I. And so this has to come from something. So let's put an n upstairs, and I need to produce an index j downstairs. So I take some n here, and then I put here the original element gmn. So that's just, let's say now the calculation rule. So now I told you, first of all, what is the, let's say, source of the rule. And then the second part of my answer was, that's the rule that comes out. Now, I'm not quite sure it actually answers the question, but in principle, that's all you need to know to do the basis transformation. You just need to know that these two essentially, I mean, now I've showed them with two examples, but there's essentially for every index that is upstairs, you need to put this. For any index that is downstairs, you need to put this. Now, of course, if you're going in the opposite direction, if you want to transform V's tilde into V, then you just do everything with the index, with the tilde and the V interchanged. So then you would, when to start, so these, remember these lambdas are given by saying what is an element of the new basis vector in terms of the old one. So that's the definition of the lambda. Now I could, of course, also do it the opposite and say what is EI in terms of the EJs. And then I better use something different symbol. So I could use also lambda, tilde, and then ij. And then I just do the same thing with that one. So I hope this gives you enough, let's say, rules to figure out in all situations what to do for the basis transformation.
Yes, thank you. That helps.
Okay, good. Okay, now I think the time is now progressed as it's one after one. So I could in principle start now with the next section. But still, I of course take questions if there are any.
Yeah, there is a question, but I'm not sure. Is in the chat. There is somebody wrote, but then you have to change the definition for tensor, right? Because we only consider T V cross V star cross to R regarding a M by N matrix. But I don't know what he's referring to actually.
Yeah, I guess probably this was referring to this previous thing where I said that the tensors can be interpreted as maps. And of course, the tensor a priori is always an element that takes as input these things and outputs a real number. So if I say that I interpret them as a map, then it's really a new definition. So you could see it as I take the tensor, which is not a map to a vector space. It's really a map to R, but I interpret it as a map from V to W. And what does it mean to interpret it? I just leave one element, one argument open. And then if I leave one argument open, what comes out is indeed a vector or a covector or whatever this argument here was. So it's not that I now change the definition and say a tensor is now a linear map from V to V. I just say I take the tensor as it was and define, it induces a linear map in that sense. I hope that helps answering that question as well.
It was actually my question.
Mm-hmm.
And it was regarding if you have instead a n times n matrix.
So now there was a sound problem. Can you again just repeat the last 5 words you said?
Like if you have a m times n matrix,
yes.
Would you have to change the definition of the tensor?
An m times n with different m and n, you mean?
Yes.
Yeah, this doesn't work. Yeah, so, I mean, you shouldn't go the other way. We have defined tensors, and tensors can be represented in terms of square matrices or even higher dimensional ones, but they will always have the same number of dimensions in each argument. So if I take a matrix which is not a square matrix, then I cannot, I mean, this doesn't correspond to a tensor. What I can, of course, do is to interpret as a square matrix by filling in the remaining elements as zeros. For example, if I can embed one space into another. But a priori, this claim is not that any matrix is a tensor or corresponds to the coefficients of a tensor. The claim is the opposite, that every tensor can, if I write down the components, be represented as a matrix or a higher dimensional thing. So if it's a tensor and 1, 1 or 2, 0 or 0, 2, then it's a normal square matrix. If it's a bigger tensor, like a 1, 2 or so, then it would be a 3-dimensional matrix, so to speak.
Thank you.
Question, or not yet.
Is it possible to ask another question about this basis change transformation?
Yes, sure, yes.
And we have said that this in the vector space, in the basis, ei tilde is equal to lambda ij ej. And then we said in the dual space,
in this relation here.
Yes.
Mm-hmm.
And then in the dual space is epsilon I is lambda ji epsilon tilde j. Right. Does it have some relation between this lambda ij and lambda ji?
Okay. Where was the second thing, this or the epsilon? I think the second thing you mentioned was epsilon I is equal to some lambda, which I would now a priori call differently. ij epsilon j. So is the second thing you were talking about this such a thing? Is that?
And yeah, it works as well. And my question is, does this lambda ij and lambda ij bar and are they related? What is the relation?
Yes, the answer is yes, they are related. So that's actually something that I think we did almost last time. So what you can do is to insert the two expressions into each other. So you just essentially say what you know is that by definition epsilon tilde I applied to some ej tilde has to be the delta function. That's the definition. If you use that and do a little calculation, which I think I did in a slightly different way in the last lecture, so maybe you can go back to the notes there, then you will find that this matrix here, which relates the dual basis vectors, is just the inverse of the matrix here that relates the basis vectors of V. So the answer is the relation is the coefficients of this matrix are given by the inverse of the matrix defined by the coefficients of that one. Does this answer your question? I mean, I didn't now again show the derivation, but maybe you can try doing it by just using that relation. So just use this and insert this thing for E, insert this thing for epsilon, and then you will find a larger expression, and then you will see that this expression can only be consistent if this thing times this interpreted as a matrix gives the identity. Does this help you?
So if we transform back from an epsilon j to epsilon j delta to epsilon I, then this matrix lambda is the same as the one in the vector space.
Yes, so it's actually the so yes, now there is something maybe I should mention as well in this context, that here, yes, there are actually four different ones a priori. One is if I go from E to E tilde, one if I go from E tilde back to E, and you will find that this one is also the inverse of that one. And here I do something different. I go from epsilon to epsilon tilde, and we will also find this one is the inverse of that. The difference is that this is also somehow a transpose. So when you write it down, you will see that here I sum, in one I sum over the, you see the first index is up and the second is down. So it will be also the inverse, but if you write it as a matrix, it will be the transpose. So the rows and the columns are interchanged. That's what you will find. So it is true that both this one and this one will be inverse matrices, but they're not exactly the same because of this different order between the upstairs and downstairs index.
Okay, thank you very much.
Okay, you're welcome.
There was one last question, but I think you already answered. It says, would it be correct to say that these transformation rules can be summed up by saying the matrix of the old epsilon basis of V star in the epsilon tilde basis is the inverse of the transpose of lambda?
Yes, I think this is correct. I don't like too much to talk about transpose because it always refers to the, let's say, representation as a matrix. But it's correct to say it like this. But, you know, if I write things in this index notation, then I don't need to talk about transposes and so, because just by the index, it's clear which one I sum over. So that's, the transpose still works, let's say, in the case when I have 0, 2 and 2, 0 tensors. If I have, we will later deal with 2, 1 and 2, 2 tensors and 3, 1 tensors. And in this case, talking about the transpose would be kind of ambiguous. So while it's correct, I would not do it normally, just to be prepared for the later more general considerations. Okay. So is everything clear at this point? Because I think it's good if you're clear about these things when you enter a new section. And again, let me encourage you to study the lecture notes in such a way that you really think that everything that is written there is not so much written there. I try to be quite concise there. But that's, you really understand in detail. So even if it's just about indices, there are details, but they're important. Otherwise, you will not succeed later in doing calculations. Okay, so differential geometry. As I said, this will not replace a course in differential geometry. I want to give you the relation to physics, and let's therefore start with physics. So if you think about what physics, or in particular general relativity, wants to do, is it wants, of course, to describe space and time. And therefore, the basic objects, if you want, that GR talks about are what we call an event, or events. So an event is really the thing that we would probably intuitively, and the name was chosen for this reason, that we would intuitively call an event. It's something that happens at a certain place at a certain time. So in physics, it will be typically something like two particles collided. And you can identify, of course, the time and the location where this happened. Now, the object that we will mostly talk about in the rest of this course is just the collection of all possible events, and that's space-time. So space-time is, on a very abstract or general level, is the collection, the set of all possible, and by possible I mean there are also events, I mean locations in space-time, or a place in space and in time where nothing exciting happened. There's just an air molecule there, or maybe not even, but it still counts as an event. So it's a collection of all possible events. That's space-time. Now you see, the idea is really we start from almost nothing. Now, if you wouldn't know how the world looked like, you would say you now know nothing. They're just events and they're in a set. So now we need to equip this with some structure. However, we want to be careful not to introduce too much structure, because that was exactly the mistake that led to theories which will not be able to include gravity. So in a way, the big step done by Einstein was to get rid of structure we would intuitively assign to space-time. Nevertheless, we need still some structure to be able to talk about it. And that structure will be provided by saying that space-time is a differential manifold. And the differential manifold is now the object that is described in mathematics by the theory of differential geometry. And that's why we are now doing differential geometry. So it's this particular object we are going to define. So by the way, so far I didn't, for example, say that space-time is R4. So that is usually the next thing you do. You would say it has 4 dimensions, 3 spatial dimensions and 1 time dimension. But that would already be something we don't want to do, and we will see later that it's also not the case. Space-time is not necessarily R4. However, it is locally R4. So if I go to a sufficiently small place, and actually our whole universe is in that sense still a sufficiently small place, not the whole universe, our galaxy, maybe without the center that is a black hole, is still such that it's in a way R4. But when you talk about R4, I mean the four-dimensional real space, you would probably also automatically think of a vector space, because we can go in certain directions. But that's also something that we will not do. In GR, we will again only do it locally. We will only say on a sufficiently small region, space-time will look as if it was a vector space in a way, but not in general. And to say all that in precise terms, it turns out that differential geometry is very useful. So it's not that differential geometry is just something that was, I mean, a priori is a good thing. We really should come from the other, let's say, direction as physicists and say, we just want to have a minimal formalism, and then it happens that these assumptions just coincide with the assumptions that are made in differential geometry. But I will want to be a bit more precise and distinguish two types of assumptions. Okay, this is not now a mathematically precise distinction because it's a physical one. I mean, the assumptions come from physics. They are not themselves justifiable with mathematics. But when we have a mathematical model of our physical world, we usually make certain assumptions that are really motivated by physics. So there are certain, so to speak, physically motivated ones. And one of the physically motivated ones is, for example, that we can measure distances in our physical universe. I can tell you that two things have a certain distance from each other. I can also measure time. I can measure the time that passes between two events which I connect. So I have an event now that I'm standing here now starting to give the lecture, and there's another event where I'm ending the lecture, and I can tell you what time passed in between these two events. So the example is that we can measure time. That's obviously something that should be reflected by the mathematical object. So far, I just told you space-time is a collection of points, of events, so there's no notion of measuring time. So we'll introduce structure that reflects the fact that we can measure time. But there are also other type of assumptions, and the other type of assumption is kind of assumptions that I would just say are introduced for convenience. And one of these assumptions, an example, is the fact that the space-time is differentiable. So what do I mean by assumptions for convenience? Maybe if you go back here, when I said there are events in space-time, then it's not necessarily true in any particular way that these events are somehow connected to each other in a smooth way. Because if I, let's say, do physics experiments and measure events, for example, the collision of a particle are just collisions at different places happening, but there's nothing in between. So if I just look at the events that I can measure, about which I can talk experimentally, they are just what one says sometimes sprinkled over space-time. So just very few dots in space-time where something measurable happened. But in between these dots, we don't have any data for what happened in between the dots. So if you, let's say as a picture, imagine that we have space-time, which I usually draw two-dimensionally because I take all spatial dimensions to be in the horizontal and the time dimension in the vertical. So by the way, x0 will usually stand for time. So if this coordinate is a time coordinate, I will of course come back to that, but just to illustrate this, so the events are just points. But there's nothing in between. There's no data for in between. Nevertheless, we mathematically describe the object as if there was something in between, as if we had kind of a fully filled object where we can kind of smoothly go from one to the other. But that's just convenience. There's no physical reason to say that. Of course, it's very intuitive to do it in a way. We think of space like that, but there's really no experimental evidence that it should be like that. And it's indeed also reasonable not to necessarily assume that if one, for example, wants to nowadays come up with a theory of quantum gravity, then exactly this assumption that the full space just exists to any arbitrary detail and it's arbitrary fields between the points is actually an assumption that is probably not allowing us to derive a theory that brings in quantum mechanics. Maybe just a remark about that as well, which is at this point maybe already quite appropriate. When we say that the basic objects of GR are events, And maybe you have heard already in maybe more popular books that general relativity is not compatible with quantum mechanics. Then this has already to do with this very basic assumption, namely that the events in quantum mechanics are not compatible with that view that they are basic objects. So in quantum mechanics, you cannot talk about events as basic objects. You could, of course, say maybe if you do a measurement, there's an event. But the universe existed before people did measurements. There were just wave functions there, or I mean, they were also not there. That's how we would describe it. But so it's not clear that in a quantum mechanical description of the universe, what the events should be. They simply are not defined. So if you take ordinary quantum mechanics and ask yourself, what is now the event if you describe a hydrogen atom? That's probably what you did in your bachelor studies. You described a hydrogen atom in quantum mechanics. What is now the event, or what are the events there? There are just no events. So it's this very basic starting point of GR that is already somewhat incompatible with quantum mechanics. So we should take everything with a grain of salt and understand that even the basic starting blocks of GR are not really things that are absolutely well understood. We could just, however, say they are very good approximations. As long as we are not caring about the quantum world, if things are macroscopic enough, then it looks as if there are indeed events. There are collisions between particles and so on. Although if you would now try to describe this collision quantum mechanically, it would just be a very smooth event with no well-defined point in space-time that we could say now the collision happened. So this is just to give you kind of also a feeling of what is just mathematics that we introduce, which is not physically justified, and what is physically justified. And the point here is the fact that we assume it's differentiable cannot be directly physically justified. It turns out to be very convenient to assume it because it enables us to use all the mathematical tools, but it also corresponds to an assumption that is not rooted in physics. However, of course, it's very well, it's a very good approximation of how we perceive at least the classical world. And that's why it works very well to make this assumption. But we should therefore also not take it too seriously. If someone now asks, is now this manifold C1 or C infinity differentiable? What is the right thing? Then I would just say, just take the choice that is most convenient for your calculations. And that's usually that it's just a smooth thing. It is infinitely often differentiable. But again, there's no physical reason for that.
Could I ask a question?
Yes, sure.
So it's wrong to say that events happen in space-time. Space-time is like all events together.
Aha, yes, okay. That's just then a terminology. It's not wrong to say that. It's just we should kind of be clear what it means. So a priori, if I say space-time is just the set of all possible events, then you could say, but you have also the set of events that actually happen, that are not only possible. For example, you have now, let's say, you look at the collision experiment of two particles, and now you could say space-time is all events where in principle two particles could collide. And this is then this R4, so to speak, locally at least. And then you talk about the actual collision event. And then, of course, what we mean by saying that this event happened in space-time is exactly that this subset of events is now in space-time. So this is a language that certainly, I mean, I wouldn't say it's wrong. It's just that we need to be clear about what we mean. And that's why I have this term possible events, in a way, to still allow for that.
Okay, thank you.
Okay. So now let's, as I said, we have not any structure so far, so we need to introduce some structures. We have just a set of points. And the first structure we are introducing is by saying that it's not only a set of points, but it's actually a topological manifold. So that's essentially the first structure we introduced. And now I need to remind you of something. namely of something you should have learned in analysis. What is a topological space? It's actually a very simple thing. That's why I can remind you in 1 minute of that. A topological space is usually given by just a set M, that's the space. For example, space-time will be a topological space, and an additional set, which I call O, which says which subset of the set M are considered to be open. So M is just a set, and O is mathematically a set of sets, and these sets are called the open sets. So for example, the usual thing if we talk about the Euclidean space is to say M is the Euclidean space, it's R3, and O is, for example, containing all so-called soft balls. So these are epsilon balls with a boundary that is not an equality but an inequality. So you say it's the set of all points that are whose distance from a given point is smaller but not equal to some given epsilon. So, and then you take the finite union or infinite unions of those and finite intersections, and that defines the set of all open subsets. I guess you have discussed that a lot in analysis, that what an open subset is, but the point is here we just take the viewpoint that we give this set, we tell somehow in a certain way these subsets should be considered open. And if I will later refer to the standard topology of R3, then I mean that this set of open sets is just the usual set of open sets that you would choose by taking these epsilon balls that I just mentioned. Mathematically speaking, it's just an arbitrary set such that it contains the whole space M and the empty set, and such that finite intersections and infinite unions of sets are again in the set. Anyway, that's something you can look up. It's not that important to understand the details there of topological spaces. There's something that is much more important, which is the notion of a homeomorphic map, which has to do with that. So what I will now define essentially, and actually the full definition is in the lecture notes, and here in the lectures I just want to actually illustrate this with pictures, which are however hopefully sufficiently clear that they contain all the relevant information. So a topological manifold is the object that characterizes now physically space-time with additional structure, and the additional structure we want to capture is the fact that the space-time is locally, that the space-time looks locally as it looks to us, namely as an object with 3 spatial dimensions and 1 time dimension. That's what is captured by this mathematical notion. So what does the mathematical notion tell us? The mathematical notion tells us the following. That will, in the future, in the next 2 or 3 weeks, often draw pictures like that. So on the one hand, we have this set of events, which is space-time, and I already draw it as like a surface. I mean, at the moment, we don't really know whether it looks like a surface, but the whole point of saying it's a topological manifold is that it will look like a surface. So the left-hand side is just space-time, and we describe space-time as a topological space. So M is the set of all events, that's space-time. And now we need to say what is O. So in other words, we need to somehow specify which things are close to each other, but not by specifying distance, but just by saying what is the open set. So maybe you remember from analysis that defining the open set somehow gives structure to a set, which tells you which things are neighboring. And neighboring things are, or you can essentially define the notion of things being neighboring or approaching some other point by having a definition of open sets. Now, the point here is that we want to say it's locally isomorphic to, or locally similar to RD. RD is the d-dimensional space that we have with the standard topology. So if I write here O standard, I mean the standard topology I mentioned before. And now the requirement is the following. If I take any event, so any point in space-time, and I look at a set U, and I look at a map from here to here. Then I require that, so the requirement is that this map, which let me call it X, should have the following property. The map should be homeomorphic, which means that it's actually continuous and has a continuous inverse. And okay, of course, it will map this point to somewhere. So the requirement now, okay, maybe I didn't now phrase this very consistently. The requirement is the following: a set of points M, or a topological space M with a definition of open sets, is called a topological d-dimensional manifold if it is true that around any point I can find an open set. I mean, there is a well-defined way of saying what an open set means because we have specified O in some way. There should be an open set, so there should be a region around this point such that I can find a continuous and invertible map, which is again continuous, into RD. So this really means that somehow, while deforming things maybe arbitrarily, but not tearing things apart, I can take this thing and make it look as if it was RD. And RD will, of course, later be R4, so the four-dimensional space. So this is weaker than saying that the whole M is R4. It's really saying just locally it has this shape, this structure. Now, by the way, what does continuous mean? Maybe you remember, if you the general definition of being continuous is that the origin of any open set should again be open. That's how it relates to topology. So it's this generalized notion of continuity that you should have in mind. So it's well defined if you have two topological spaces, this one and this one, what continuity means. Okay, so that's what the topological d-dimensional manifold is. So it sounds like a very complicated object, but what it actually is, it's just a set of points that locally look like RD in that sense.
There is a question in the chat. Yes. They're asking whether it's needed to have a Hausdorff space-time. So they ask if it needs to be Hausdorff as well.
Yes, so you see, you essentially have all the properties induced. So the requirement that it's homeomorphic to RD will just induce essentially the same topological properties of the standard method. So here I just take the standard topology, which is Hausdorff, and so it induces that on the manifold. Now the question is, could one relax that? For the moment, I don't want to assume that. I really want to assume it's just homeomorphic to the standard topology, and therefore Hausdorff. I hope this answers the question. Okay, now there is... yes?
Yeah, it says that's not true. Removing the Hausdorff assumption makes the line with two zeros a manifold, but it's not itself Hausdorff.
Sorry, can you say it again? Or, okay,
so it was me who wrote that. Yes. So one of the standard examples of a non-Hausdorff space is the line with two zeros. And if you just drop the assumption a manifold has to be Hausdorff, that would be a manifold, even though like every point has a neighborhood that's homeomorphic to a neighborhood in Rn, or in R, I guess in this case. The thing itself would still not be Hausdorff. I don't think you can just...
Oh, you were saying that the manifold, so despite the fact that this is Hausdorff,
yeah, because the issue is
necessarily true that this needs to be Hausdorff as well.
Yeah, well, the U itself would be an open set that is Hausdorff, but the entire space wouldn't be Hausdorff because you only require that, like, for each point there exists some neighborhood,
you're
but
right.
not all neighborhoods.
Yes, you're right. It's only locally Hausdorff in that sense. Yes, yes. So the whole thing is not necessarily. That's what you're saying. The whole M is not.
Yeah, so like...
Yes, okay. But that I will also not require. So indeed, what I require for all our treatment is indeed only locally it has to have this structure. Yes, so in that sense, it doesn't need to be. Maybe we'll come back to that once it will become necessary to make these distinctions. But for the moment, we only require this, the local structure, so we don't do anything. Okay, I hope that clarifies it for the moment. And okay. Suppose this is the case. Then let me introduce one more terminology, which is that X, so these two things that I specified, the region U, so around, I specify the region and I specify the map, and this will be called a chart. So a chart is just essentially the object consisting of these parts, where the first thing is called chart domain, and the second thing is called chart map. And okay, one more terminology. X, so X is this map, this chart map, defines a D-tuple of coordinate functions. So the coordinate functions are just, I mean, that's the obvious thing, because if I have a chart that goes into RD, that's equivalent to say that I define D functions, namely for each coordinate. And each function is therefore a function that goes from this region U to R. I'm not saying more about that for the moment. This is just terminology we'll use later. And then finally, I will call something an atlas. An atlas is essentially a set of charts whose domains, so you know what the chart domain is, it's this U, whose domains cover in the whole manifold. So you can really think of the atlas as actually an atlas as you know it from geography, because what it does is it consists of pages in the atlas, and each of these pages probably contains a chart or several charts. And of course, the atlas of the world should be such that if you would take all these charts together, I mean, the charts usually only map a part of the world, for example, Switzerland or the US or so. But if it's a good atlas, and if you take all these charts together, you will be able to cover the whole surface of Earth. Of course, something will be double and so on, but at least it should cover the surface. And that's exactly the idea here. So there's one more notion that I want to introduce, which is that of a chart transition map. And that's maybe the last thing to do for today. So let's suppose I have two chart maps. So I have here region U, and this region has a chart map X that goes into RD. So there's this region X of U, that's the image of the region. And let's suppose I have another chart which overlaps, whose domain overlaps with the domain U. I call it V. And it has also a chart map, which I call Y. And it maps it to another, again, to RD. So the things on the right-hand side should be RD. Then, in this case, I also have an overlap. So let me indicate it by red color. So this is an overlapping region. And of course, this overlap will also be mapped here to something here and something here. So the red thing here is X of U intersected with V. And this is Y of U intersected with V. And this here is just U intersected with V. Now, one important object that we will study is how do you get from one coordinate to the other? So if you have here something in the red region, a point, you can get to the corresponding representation of the region in the other chart. So the red region is covered by two charts. It's like in an atlas, and there are overlaps, like there's maybe Switzerland, but there's the boundary also with Austria, and the chart for Switzerland and the one for Austria, they will probably overlap. And so this defines an operation, and mathematically this operation is just Y applied after the inverse of X. So you take the inverse of X, you go back to the manifold, and then again to Y.
Excuse me? There is somebody yes, asking whether you can scroll down a bit the right part.
Oh, yes. Yes. I hope like that everything should be visible now. So this combined map is called a chart transition map. And now, let me just now at the end of the course, briefly come back to physics. Again, so a chart transition map will correspond to the change of coordinate systems. So how should you think of this? So in special relativity, the thing that I've drawn on the left is actually space-time in special relativity is kind of flat, so I draw it as something flat. And in this flat space-time, we can, of course, still use different coordinates. So let's suppose we have stuff happening in this flat space-time. So there's, for example, a particle flying here in this direction. So, of course, what we call world line, that's the set of events where the particle is. And that's, of course, now a line in space-time. And we could have another particle that flies in another direction. And now we could have representation. So in special relativity, we usually take as charts which cover the whole space, because the whole space is just R4. But we still have different charts. So we could have a blue chart, which is chosen in such a way that the blue particle just corresponds to this time axis. So it remains at position 0. And then in this chart, the green particle will look probably something like this. But then you could have another chart map, which is adapted for the green particle. So in this chart, you also take the whole map and map it to the chart. And in this chart, maybe the green world line is just at the position x equals 0. And the blue one now looks different, for example, like this. Now, what we do generally in relativity theory, so that's now a different chart, in special relativity. So in case you have already done special relativity, what you usually do is to actually transform between different charts. So to transform between this chart and this means physically that we are first looking at the world from the point of view of a coordinate system in which the blue particle is at rest. And now we are going to a coordinate system where the green particle is at rest. And so in this differential or in this geometric language, that's just the chart transition map. So what you know as, for example, Lorentz transformations, which is actually transformations to go from here to here, corresponds in this general language to a chart transition map. Now, because we are very early in this course, and it's impossible to give exercises on GR, I have included something on special relativity. The idea is not that you already need to know special relativity. There should be kind of self-contained these things, but the only thing you need to know is the following. In special relativity, you have one requirement, namely that if you have a light ray, the world line of light, and if I draw it into these charts, then it will always look like a 45 degree line. And that's a requirement. I mean, that's kind of the requirement that the speed of light is constant. And what you will see, or what you can verify, is something that you have probably already done in the past, but it's very good to remind yourself that if you take this as a condition that the light should have constant velocity, then the only transformations which are possible, the only linear transformations, if you only look at linear chart transition maps, are the so-called Lorentz transformations. That will be an exercise of this week's exercise series. So maybe I should add that in general relativity, we will usually have maps which are not linearly transforming. In special relativity, we only look at inertial systems. And this is important, inertial systems are exactly linear chart transformations. A line that is straight will remain straight. But if you choose more general coordinates, for example, if you look at a coordinate system from the viewpoint of an accelerated observer, then from an accelerated observer's viewpoint, as we have seen in the example of the elevator, one line which looks straight in one chart may not look straight in another part. So in special relativity, we are actually doing two things. On the one hand, we are restricting ourselves to a kind of flat space-time, but at the same time, we are also restricting ourselves to chart transition maps which are linear. And as I said, this corresponds to the requirement that we are only looking at inertial systems that enforces this linearity. I will later in the course come back to what is special about special relativity. But one thing that is also important for later is that we will usually express things in terms of a variational criterion. So instead of saying a line is straight, which may not look straight depending on coordinates, it's always good. It's an equivalent characterization is to say it's the shortest connection. And one of the exercises, I think it's the second one as well, you will calculate essentially the movement of a particle in flat space-time according to such a variational principle. So that's just a short outlook to the exercises and to make sure you understand the connection of them to the lecture. But after all, the purpose of the exercises is also to make yourself a bit familiar with the tensor calculus. So when you do this Lorentz transformations, try to use the terminology and notation we have introduced here. Okay, that was it for today. Thanks for your attention and thanks for the many questions. I really appreciate that. As usual, I will stay a bit for the questions, but for those who leave, I wish a nice weekend and I hope to see you again next week.